Good morning, good afternoon, good evening to Prof. Amiris. So we are from the group Drone. So our team is made up of three members. So first one is Kalian, second is Gan Liang, and third is me. My name is Sun Yong Yi. My metric number is 222963. So later on, I will proceed with our task and some overview of our jobs. Okay, here is some overview of what I have done. It basically is a summary. We will go through it in detail later on. Okay, the first step, we have to know that our audio or our signal input, it is a low frequency input. So in this case, we apply the stereo to mono method. So the stereo to mono method means that we convert the two channel to one channel matrix. So in this case, the low frequency component are center between the first column and second column. In this case, the first column and second column, they are identical. So we only take one column. We can get all the input from the song. We can get all the signal from the song. So we don't need to spend more calculational power or calculating power or computational power to uh, to do to do the repeated job. So this is not that a constrict redundancy. This is not a redundancy. So if you look at the mallet code, we the first line, the size data two means that the system is identifying is detecting both the channel, but the result is it only take the first column, which is data one. That means it decide that we only take the data from data one from the column one. Okay, so here is our output. So I will start with the peak oscillar value in the next slide first. Okay, to detect the positive and negative half cycle, we use the max absolute data, which is the first line of the output part of our mallet code. In this case, we have the result of the peak amplitude is negative 0.4498, which is located in the negative half cycle, and the time it happens, which is 2.12 seconds, like that. And after that, we have the peak energy frequency, which is it happens in 107.67 hertz at time 10 seconds. So this is our value. Previously, we already known that the red color means a very high power density, while the blue color means a very low power density. So in this case, we can see the red color is accumulated in the bottom part. So previously, the command window tells us that the peak energy frequency is 107 hertz. So if we focus on the 0.1 kHz, it's known that the region along 0.1 kHz, the color is red. That means this tally with the spectrogram, the output before is tally with our spectrogram, the energy is accumulated in the 0.1 K region. So this also gives us another signal or info that the song is mostly low frequency component. This is why we can use the acoustic redundancy. That means we only take one of the channel. If the song is has a higher frequency, or it has a frequency larger than 500 hertz, we have to use another method. So this is why our method is absented in this experiment, since the audio is mostly low frequency component.
Okay, then let us continue to equalizer architecture. So first, actually for the equalizer design, we implement a three-band system using the FIR filters specifically for their linear phase properties, which ensure that the audio signals does not suffer from phase distortion and their inherent stability. So actually, we selected a filter order of 300, which provided a sharp enough transition between the frequency band to isolate the bass, mid, and treble effectively without requiring excessive processing power. So I also show the flow chart at there. So actually, we use the three-band FIR equalizer design. So next, then for the frequency band, we have divided to three band, which the base is 20 Hz to the 250 Hz. The mid band is the 250 Hz to the 4K Hz. Then the treble is 4K Hz to the 20K Hz. So in MATLAB, we normalize this frequency against Nichols length. So the final output is calculated using the wedge summation equation shown here. So where the G represents the gain applied to the base, mid, and the treble component respectively. Then for the gain setting, we choose a boost the base by the factor of 1.8 to enhance the low end rhythms. So while slightly attenuate means decrease the treble to 0.7. However, the signal can be lead to the digital distortion. So to solve this, we implement a creeping prevention. So the algorithm is the system can check if the maximum amplitude exceeds 1. If it does, so if we normalize the entire signals, then the relative to the peak ensure the audio stay within the safe digital range, so it can prevent the creeping lah. Then we also have three port. Then this port verify our filter design. We can see the bass filter on the left passing only low frequency, then the mid filter in the center, and the treble filter on the right. So the port confirm that our order of third 300 achieve the desired sharp roll off, as there is a clear separation between the band which no the unintended overlap. So this validate that the mathematical design work is intended. Then finally, we comparing the original and equalized signal in the time domain. We see the increased amplitude reflecting the bass boost. Then crucially, the signal is not crippled, so the spectrogram provide a stronger proof of success. So if you look at the bottom axis, the energy density has increased significantly in the low frequency range with the baseband, so matching our 1.8 gain setting. So this confirm the equalizer successfully alter or change the audio profile. Thank you.
Okay, so welcome to the system and testing part. So first, I will simulate the GUI interface, and we have the input from two sources. There was the music and audio. Okay, so after simulation, I will explain more about the architecture of the GUI and also explain our result. So we are from group drone. So this audio is for testing for the real-time equalizer. So we are from group drone. So this audio is for testing for the real-time equalizer. Okay, so now I will explain the real-time GUI optimization and architecture. This was the core part of the GUI design. So whenever we design the real-time GUI, the bigger challenge we face is we want to enable real-time interaction in the cloud environment. Because we are using Meta Online, not using software. And another challenge is the filter we use on part 2 is FIR filter. But the drawback is the computation is very slow because whenever we use the FIR filter, we need to use the order equal to 300. But whenever we use the IIR filter to replace it, we only need to use the IIR second order Butterworth filter. So as a result, this the significant can lower the computation loop. So in this GUI, to make sure the speed, we use the pre-calculation first. The raw audio is pre-filtered into 3 isolated streams. There was the bass, middle, and treble, and they were stored in the RAM. So whenever we move the slider, it triggers a simple weighted summation. So this can make sure the result we get is zero latency. So as you can see, the core missing algorithm, this is the summation of our result. Okay, so now I will explain about the core algorithm implementation. I only choose the most important part in my code. So the first one is the pre-calculation. So this is what I explained just now. We use the compute once and mix many algorithms. And the second part is the real-time mixing. So the formula, as you can see, this is the formula I showed just now. And what we add on the code is the safety net because we want to ensure the amplitude does not exceed 1.0. So the peak although we adjust the slider, but the peak will not exceed 1.0.